Welcome to a new lecture on structural analysis. So, in this lecture, we will be dealing with train of loads, another problem on train of loads. So, the problem selected for this lecture is shown in this slide. If you see, the problem is a system of moving loads crosses a girder of span 60 meter, simply supported at both its ends. The magnitude of the load in the system are 100 kilonewton, 200 kilonewton and 50 kilonewton. The loads are equally spaced at a distance of 2 meter, and you are supposed to find out two things. First one is you have to determine the maximum bending moment in the girder, and the second thing is you have to also find out the maximum bending moment under the load having the magnitude 50 kilonewton. So this is a usual question that you can see in your university examinations. And the procedure for both these cases, that is to determine the maximum bending moment as well as to determine the maximum bending moment under a given load, is almost same. So first of all, let's have a overall view on how to proceed this problem. Okay. So in step 1, what you have to do is that, since this is a case where you are supposed to find out absolute maximum bending moment and bending moment under a single point load, first of all, you have to find out the resultant of the train of loads. Okay, that will be our first step. So basically, you know, in the case of train of load, all the loads will be parallel to each other. So in order to find the resultant, what you have to do is just take the sum of these loads. So that will complete our step 1. So once you have done that, in the next step, what you have to do is, you have to basically find the position of the resultant with respect to any of the loads. So once you know the magnitude of the resultant, in the next step, we will fix the position of the resultant, or we will find out where the resultant is actually acting. And for this, we will take the help of any other load. So we will say that our resultant is acting at a distance of, say, x units to the left or right of any of the specified load. So we will see these things in detail when we proceed. And once you complete that step, in the next step, what you have to do is that, based on the function that is asked to be found out, you have to finalize the position of the train of loads, and you have to place these train of loads on the span of the beam. Okay. So once you complete that, once you have found out the position of the loads on the span, in the next step you have to draw the influence line diagram corresponding to the function which is asked. And after drawing the influence line diagram, you have only 2 more steps, where in the first step you have to find out the ordinates coming in the influence line diagram below each of the concentrated loads. Then you can directly calculate the required function by multiplying the magnitude of the load with respect to the corresponding ordinates which we have calculated. So now let's proceed with the problem. So as mentioned, for both the cases, that is to find the absolute maximum bending moment as well as to find the bending moment under 50 kilonewton load which is asked in the question, you need to find the resultant, and also you have to locate the position of the resultant. So let's see how to do that. So basically we have 3 loads in this case. First one is 100 kilonewton, second one is 200 kilonewton, and the third one is 50 kilonewton. So as I have already told you, in order to calculate the resultant, what you have to do, since they are parallel to each other, you can directly take their sum. So that will be 100 plus 200 plus 50, which will come around 350 kilonewtons. Now we know the magnitude of this load. So what remaining is, you have to find the position where this load will be acting. That is, the resultant will be acting. So for this, I am arbitrarily assuming that my resultant R is acting at a distance of x unit to the right of my 100 kilonewton load. This is just an assumption. You can take any of the load as you like, and you can assume that our resultant is acting at a distance of, say, x units. So once that is done, then in order to calculate the value of this x, what you can do is that you can use a simple principle which you have already learned in engineering mechanics. That is none other than Variance theorem. So if you remember back, what was Variance theorem? It states that the moment of the resultant about any point will be equal to the algebraic sum of moments of each of the folds about the same point. So I am just applying that. First of all, I am trying to take the moment about this point. If you see in the slide, I am going to take the moment about this particular point. So first I am calculating the moment of the resultant, that is this R multiplied by this distance, that is x. As per our assumption, it is x meters. Okay, so the moment will be R into x, and this can be equated to the algebraic sum of moments of each of these forces about the same point. Okay, please note, about the same point. So Once we calculate the moment, we will obtain it as 100 into 0, that is 100 multiplied by 0, there is no distance here. Second load is 200 and it is at a distance of 2 meters, therefore the moment will be 200 multiplied by 2, and the final load 50 is at a distance of 4 meters. So the moment will be 50 multiplied by 4. So these things can be equated as per our variance theorem. Therefore, once you equate this, please note you already know the value of R, which was 350 kilonewton. We have already calculated that. So substitute that value and you can easily find the value of X. So on the RHS, you will obtain it as 600, and right now what I am doing is I am just bringing this R to the other side. Therefore, my X will be equal to this 600 divided by R, or in other words 600 divided by 350. In this particular case, you can see that this value will be coming around 1.714. What does that mean? That means our resultant is acting at a distance of 1.714 meters to the right of my 100 kilonewton. So if you see this, you know that the distance between 100 and 200 itself is 2 meters. So our resultant must be in between these loads, and it must be nearer to 200 because the distance X is obtained to be 1.714 meters. I hope that is clear for you. Now let's proceed further. Now we are moving to each of the case. In the problem, there were two cases. In the first case, we were supposed to find out absolute maximum bending moment. So let's see that. So as we have seen earlier, in the next step what we will do is that we will have to finalize the position of the train of load on the span of the beam. So for that, since in this particular case we are supposed to find out absolute maximum bending moment, we need to satisfy a condition. In order to get the absolute maximum bending moment, what you have to do is that, say it is given here, absolute maximum bending moment will occur under the load which is near to the resultant of the load system. So if you go back, we have already seen that X was 1.714. So this resultant will be near to 200. It will be somewhere here. So the nearer load to this resultant is 200 kilonewton. So we will consider 200 kilonewton as our critical load, and we can make sure that our absolute maximum bending moment will come under this 200 kilonewton. And one more condition is there, that is, to get absolute maximum bending moment, we have to place the critical load and the resultant equally distant from the center of span, and this is shown in this figure. If you see this, our three loads are there. Then I have also shown the resultant, that is 350 kilonewton, and right now what we have to do is that we have to ensure that this mid span or this point is at the exact center of this distance. So basically this 350 kilonewton and 200 kilonewton must be kept at equal distance to the left and right of the midspan. That is what we have to ensure in order to get the absolute maximum bending moment. So now let's see that. Say as per our calculation, X was obtained to be 1.714. So the resultant will be, actual position of the resultant will be like this, and from this diagram you can see that this total length was 2 meter. If you subtract 1.714 from 2, you will get the distance between our resultant and 200 kilonewton load, and in this case it is coming around 0.286. So in order to satisfy our condition, what we have to do is we have to keep this resultant and this 200 kilonewton at equal distance from the center, and this distance in this case will be 0.286 by 2. I hope it is clear for you. So this is the position of the load. So once we finalize the position of our resultant and 200, we already know the distance between 100 kilonewton and 200 as well as this 250. So based on that, you can keep the other loads. So this is the finalized location for our train of loads. So once you complete this, in the next step what we are supposed to do, we have to draw the influence line diagram corresponding to the required function. In this case, we need to calculate the absolute maximum bending moment. So basically we have to draw the influence line diagram corresponding to bending moment, at which point, and again please note, as per the condition, absolute maximum bending moment will occur under the critical load, and in this case critical load was the load near to our resultant, and in this particular problem it is 200 kilonewton. So basically what we have to do is we have to draw the influence line diagram for bending moment at this particular point, and it will be, you know, it will be a triangular, it will be having a triangular profile as shown in this slide. So this will be the influence line diagram. So once you draw the influence line diagram, we need two more steps to complete this part. In that, the first part is to calculate all these ordinates which are coming below the concentrated load inside the influence line diagram. I have marked it as x1, x2 and x3. Now the thing is how to find these values. What will be the value of x1? What will be the value of x2 and x3? So basically you know one thing, the maximum ordinate in the case of influence line diagram for bending moment is having a general expression, that is a into L minus a divided by L. So if you see, this is our equation, and in this what is A? A is the distance from the left support to this peak point. So in this case it will be 30.143. How I obtain this value 30.143? That is basically, if you see, D is the midspan of the beam, okay, or the girder, and you know that the total span is 60 meters. Therefore the half of the span will be, that is AD will be 30 meters, and you know that this distance is 0.286 by 2, that will come around 0.143. Therefore this total distance will be 30.143. So once you have the value of A, you already know the value of span L. Substitute these values and you can see that x1 will be coming around 15 meters. Okay, so in this case we have found out the value of x1. Now what remaining is we have to calculate the value of x2 and x3. For this you can use the similar triangles. Say let's take the example of x2. In order to calculate x2, what you can do is you just consider these two similar triangles. This larger triangle formed by x1 and this smaller triangle formed by x2, and this, if you see, x2 by x1 x2 by x1 will be equal to this smaller base divided by this total length. That is, this smaller base can be seen here, it is 28.143 divided by 30.143. Therefore I can equate x2 by x1 as 28.143 divided by 30.143. So let's see that. So here I have written x2 by x1 is equal to 28.143 divided by 30.143, and from this you already know the value of x1. x1 was obtained to be 15 meters. So please substitute that and find the value of x2. So in this case x2 will come around 14 meter. Now what remaining is how to calculate the value of x3. You can use a similar method, but you have to consider these two similar triangles. This triangle formed by x1 and this smaller triangle formed by x3. So again apply the rule of similar triangles and you can see that x3 by x1 is equal to this smaller base, that is this side divided by this total side. Substituting the values, we will get x3 as again 14 meters. So you can avoid some of these calculations. If you see this figure, you can see one thing. This 200 is coming at this location and both these loads are symmetrically kept over that 200 kilonewton. So what you can do is that once you find the value of x2, it will be same as x3, because due to the symmetry in which we have kept our load. So in this case also, after substituting the values, you can see that these values are coming as 14 meter itself. So after getting the ordinates, what remaining is to calculate the required quantity. So in order to calculate the absolute maximum bending moment, now what we can do is that you just multiply 100 kilonewton with x2, add that to 200 kilonewton with x1, again add that quantity to 50 kilonewton to x3. Now we have all these values, substitute it, and you can see that the absolute maximum bending moment will be coming around 5100 kilonewton meters in this case. I hope the procedure is clear for you. Now let's move on to the second part of the question. So basically in the second part, we have to find out the maximum bending moment that is coming under a specified load, and in this case the load which is specified is 50 kilonewton. So basically when this train of load is moving from one side to another, at some particular point we will have a maximum bending moment below this 50 kilonewton. We have to find out that value. How to do that? So again it is similar to the case 1 where we have calculated absolute maximum bending moment, but there is slight difference. In the case of absolute maximum bending moment, in order to get the maximum bending moment, what we have done is we have kept our resultant and the critical load equally distant from the center. But in this case what you have to do is that you have to keep the resultant and the load below which you require the bending moment equally distant from the center, as we done in the case of absolute maximum bending moment. Here what we are doing is we are just keeping the resultant and the load below which you require the maximum bending moment equally distant from the center. If you see this figure, it is pretty clear. Our resultant 350 is coming near to 200. I have kept that here. And suppose this distance is x units, we have to keep this 50 kilonewton at a distance of x units itself. Since we know the dimension or the distance between this 100 and 350 and all the dimension between these two loads, you can easily achieve this. You can easily place this 350 kilonewton and 50 kilonewton equally distant from the center. And in this case, when you keep these things, you will obtain that this total distance, that is the distance between 350 kilonewton and 50 kilonewton, is coming around 2.286. Therefore, the equal distance at which these two loads must be kept is half of this value, that is 2.286 divided by 2, and you have to keep the load as shown in this figure. So once this is done, again the procedure is similar to what we have done in the case 1. So let's see that. In the next step, we will be drawing the influence line diagram, but there is a slight change. In this case, we have to calculate the maximum bending moment that is coming below this 50 kilonewton. Therefore, we have to draw the respective influence line diagram, which is for finding out, or which represents the bending moment below this point, and it will be having a profile like this. And again, this is the maximum ordinate, and the ordinate below 200 is marked as x2, and ordinate below 100 is marked as x3. Okay. So once you finalize this location and you have completed drawing the influence line diagram, we have to calculate the ordinate values of this ordinate. How to do that? Again, in this case, this is influence line diagram for bending moment. Therefore, this maximum ordinate will be having the same expression, that is a into L minus a by L. And in this case, a will be, as mentioned earlier, a is the distance from the left support to this peak point. And in this case, you can see that it is coming around 31.143. Substitute the value and find the value of x1. In this particular problem, x1 is coming around 15 meters. So once you know the maximum ordinate, you can easily calculate the value of x2 and x3 by considering these similar triangles. First of all, in order to calculate the value of x2, you have to consider this bigger triangle formed by x1 and this smaller triangle formed by x2. Now you can take x2 by x1 will be equal to this smaller base divided by this total length. Substituting the values here, you will get x2 as 14.04 meters. Similarly, you can consider this larger triangle formed by x1 and this smaller triangle formed by x3, and you can easily calculate the value of x3 also. In this case, x3 is coming around 13.07 meters. So once you complete the value, finding out the value of this ordinate, only thing remaining is just take the product of magnitude of the load with respect to the corresponding ordinate and add it up. That will give you the required quantity. In this case, you are supposed to find out bending moment below 50 kilonewton, that is the bending moment at maximum bending moment at this location, and it can be easily calculated by multiplying 100 with respect to x3 plus 200 multiplying with respect to x2, and finally add it to 50 multiplied by x1. Substitute the values and you can see that the maximum bending moment that can come under 50 kilonewton in this case is 4865 kilonewton meters. So please understand, this maximum means when this strain of load move from one support to other, the bending moment under 50 kilonewton will be having different values, and at a particular location what will happen is that this value, that is the bending moment coming under 50, will be maximum, and we have found out that value. For that, we have kept the resultant and the required load as per our condition. So this is how you do a problem like this. So we have discussed two things. First one was to calculate the absolute maximum bending moment, and second one was to calculate the maximum bending moment that can occur under a specified load. The main thing that should be noted here is that in the case of absolute maximum bending moment, you have to keep the resultant and the critical load. Critical load means the load which is very near to your resultant, equally distant from the center. In the second case, that is when you have to find out the maximum bending moment coming under a particular load, you have to keep that particular load and the resultant equally distant with respect to the center. Then you can do the remaining things, which are pretty simple. Thank you.